Let's take a look at this VJC 2021, paper 2, question number 1. Part 1, we are supposed to be sketching two graphs. First, the graph of y is equal to fx, then the graph of y is equal to 1 over fx. For the graph of fx, we are going to be sketching based on a transformed version of a ln function. And I'm going to press this into the calculator to just give me an idea of how this graph looks like. Although our advantage will be if we can actually memorize and derive it from the original basic standard ln graph. But let's take a look at it on our graphing calculator. So on the calculator, we have this. Okay, and based on what I see in the calculator, it is not an actual representation of the ln graph that we are expecting, right? Because this calculator has truncated this portion of the graph, okay, which we know that it is supposed to continue. How do we know that it is supposed to continue? Because this was a ln graph. This was derived from a ln graph. And looking at the expression that is given, ln 2x plus 1 plus 5. Ln 2x plus 1. If I were to let 2x plus 1 be equal to 0, then we will actually derive a vertical asymptote. X is equal to minus 1 over 2. Which means that this part of the graph is going to tend towards x is equal to minus 1 over 2, which is going to be a vertical asymptote. The graph should continue here. And there's another problem that I realized when I try to press this into the graphing calculator, which is this portion of the graph that is on the negative x-axis side is very, very much compressed. So if I were to try to do some zooming in order for me to look at the details of this part, it actually drains from me more time as compared to me just doing an analysis of this based on the ln graph. So I think I'm not going to depend so much on my graphing calculator. I'm going to just, of course, I have the shape of the graph, but I'm going to take a look at the shape and I'm going to sketch this based on also my knowledge of the ln graph. So let me sketch in the x-axis, which is this, the x-axis. Let me sketch in my y-axis. So this will be y-axis. It has a vertical asymptote, and that is like what we have discussed. X is equal to minus 1 over 2. So let's say it is here. Here, x is equal to minus 1 over 2. And based on the shape that we are looking at, the graph is going to be cutting the x-axis at the negative point and the y-axis here. So my graph is going to be like this. Okay, so here you will tend towards the vertical asymptote, then you will be cutting at the negative x-axis side, and the graph will continue all the way until positive infinity. And this is the graph of y is equal to fx. We need to indicate the coordinates of this point and this point. Okay, for this particular point here, it is easy enough for me to get it from the graphing calculator. So I'm going to do that. Let me press trace, 0. Enter. So the cursor will be tracing the graph and going to the place where x is equal to 0. And y, the corresponding y coordinate is 5. So this point here is 0, 5. As for this point, because like what I was saying, I find it very draining, time consuming in order for me to just keep zooming to find the x-intercept of this point. So I'll rather just calculate it. So for this point here, I'm going to be letting y to be equal to 0. So I'm going to be letting fx to be equal to 0, and fx is given to me as ln of 2x plus 1 plus 5. This is equal to 0. So ln of 2x plus 1, this is equal to minus 5. 2x plus 1, this is e to the power of minus 5. X is going to be e to the power of minus 5 minus 1 over 2. So this will be the x coordinate of this point here, which is e to the power of minus 5 minus 1 over 2. The y coordinate is 0. So this is my graph of y is equal to fx. We are supposed to sketch the graph of y is equal to 1 over fx. And this is a pretty unique case here, a unique question here, because usually we don't possess, usually we are not going to be given the expression for fx. But this question actually gave us the expression for fx. So why not? Let's try to make use of our calculator. So let's see whether we can get a glimpse of how the graph of 1 over fx looks like. And how I'm going to be doing that is I'm going to go back to my graph. I'm going to go back to my graphing calculator, and in y2, I'm going to attempt to press in 1 over fx by going for 1 in the numerator, and as for the denominator, of course, we can press this entire thing, or we can just simply press alpha trace and select y1. So it will give me 1 over fx. Let's take a look at the graph. Okay, and sadly, the graph that I'm seeing here is also very, very much compressed. Of course, we can zoom in to take a look at the details, but like what I was saying, it is just not worth it if I were to be doing this in an exam. It is probably faster if we were to just do our own analysis. So let's try to sketch the graph of y is equal to 1 over fx based on the original graph of fx. So I'm going to make use of the process that we have discussed on the Achevas TV. First, I'm going to look at the xy intercept, and then I'm going to look at the, actually first we are supposed to be looking at the asymptotes. So let's take a look at the asymptote. There's only one asymptote from the original fx. So for the vertical asymptote, it is going to be giving us a x-intercept. So the graph is going to be starting from here. And then let's move on to the second part. According to the Achevas TV, the second part is to look at the xy-intercept. X-intercept will become a vertical asymptote. So from here, we will have a vertical asymptote. Okay, my line is not exactly that vertical, but you guys can get it, right? Okay, it's a vertical asymptote, and this vertical asymptote will be x is equal to e to the power of minus 5 minus 1 divided by 2. And as for this point here, it's going to become 0 and 1 over 5. So maybe it is going to be, let's say here, 0 and 1 over 5. And after we have finished analyzing the original asymptote, after we have analyzed the original xy-intercept, I will just continue with my analysis from the left to the right. All the way to the left, the graph is going to be starting here. And as it progresses towards x is equal to e to the power of minus 5 minus 1 over 2, I'm going to poke a point that is, let's say, here, and I'm going to assign an arbitrary coordinate to this point. An arbitrary coordinate, okay? So it may not be actually this number, but it's just for my imagination. So a point that is here on the original graph can maybe have a coordinate of something that is less than this, okay? So I'm going to just indicate it as this, a number that is slightly less than. So I use this small little negative sign, okay, to just tell myself that, okay, it is a number that is slightly less than, slightly to the left-hand side of this. And as for the y coordinate, because it is very close to the x-axis and it's a negative number, so y coordinate, negative 0.01. So when it goes through this 1 over fx transformation, it is going to become, the x coordinate remains the same, so it is going to be this. As for the y coordinate, it's going to be 1 over this, which is minus 100. So it gives me an idea of where this point is going to be transformed, and it's going to be somewhere here, slightly to the left-hand side of e to the power of minus 5 minus 1 divided by 2, and the y coordinate is minus 100. So from here, I'm going to join to this point. So from here, joining to this point, and my graph is tending towards the vertical asymptote. Then after that, as it moves to the right-hand side of this point, again, I'm going to give an arbitrary coordinate to a point that is, let's say here, just slightly to the right-hand side of x is equal to e to the power minus 5 minus 1 divided by 2. So for this point, I am going to try to assign an arbitrary coordinate to it too. So since it's a little bit to the right, it is going to be this plus. As for the y coordinate of this point, it is going to be positive 0.01, which means that after it has gone through the transformation, it will be e to the power of minus 5 minus 1 over 2 plus, and this transformed to 100. So it's going to be a point that is slightly to the right hand side of this, and it is a super big positive y value. So let's say it is here. And from this point, it is going to be connected to this point. So let me continue from here. It's going to be connected to here. And finally, this portion of the graph, I'm going to go for a point that is here. Again, I'm using the same strategy that, that we have discussed on the Achevas TV. So this point here, an arbitrary coordinate that is assigned to this, from like what I can see, it has a very big positive y value, and it has a very big positive, x value and a very big positive y value. And this will be transformed to 100, remain the same. And this is 1 over 100, so 0.01. So it's going to be a point that is, let's say, here. Okay, positive 100 and 0.01. So I'm going to connect this over to that point, which indicates to me that, hey, you know, an asymptote exists here for the graph of y is equal to 1 over fx, and that is y is equal to 0. But this particular graph has a very interesting feature that I have still not yet placed onto my solution here, because I will be losing 1 mark, okay, if I were to leave my solution as this. And where is the problem? The problem is actually this portion over here. Because in this portion, unlike this, okay, this is actually going to continue. So I'm not going to do anything to this part of the graph, but for this part of the graph, it actually stops. How do we know that it stops? Because this is 1 over the original fx. And is there any fx to the left-hand side of x is equal to minus half? There's none. Because there's no fx for the reciprocal to take place. That is why the graph has nothing that is on the left. So this cannot just suddenly stop here. This must be indicated as a stop with a either solid dot or a hollow dot. So we do need to perform an additional analysis. Should this be a solid dot or should this be a hollow dot? Let's take a look at the original x coordinate. It is x is equal to minus half. And what is the corresponding fx? When x is equal to minus half, it is a vertical asymptote, so the corresponding fx is nothing. We cannot find any fx when x is equal to minus 1 over 2. So what is 1 over nothing? Nothing, because there's nothing for the reciprocal to take place, which means that the graph can sort of like go nearer and nearer to this point, but the graph will never exist as an actual point when x is equal to minus 1 over 2 for this graph of y is equal to 1 over fx. So for this point here, it is ending, and it is not going to be taking up the value of this particular x coordinate. So this is going to be a hollow dot. And this will help me to finish up and complete the 2 graphs that are asked for me from part 1 of the question. Let's move on. Let's take a look at part 2. In part 2, we are supposed to describe transformations. Part 2, describe a sequence of transformation that is going to be transforming the graph of y is equal to, let me just write it down here, y is equal to, I'm doing part 2, y is equal to ln of minus 2x. Okay, we are supposed to transform this through a description of 3 transformations to the graph of y is equal to fx. Let me just write down the expression for fx also. So this is going to be equal to ln 2x plus 1 plus 5. So this is going to be transformed to this. Again, we are going to make use of the sequence of transformation that we have discussed on Achevas TV, and the way the transformation takes place follows a certain description. We are going to use those descriptions. Of course, you can use your own words for description, but my suggestion is just take the official descriptions that are given to you by your schools, because they are actually really, really precise. Okay, so let's learn the best. So from here, we are going to carry out our transformation by replacing x. Okay, let's do that first. So I'm going to replace x, and I'm going to attempt to get this 2x plus 1. The first replacement that I'm going to carry out is to replace this x here by minus x. So if I were to replace x by minus x, then it will be this, which will give me a ln of 2x. So if I were to replace x by minus x, what is the transformation? The transformation is a reflection about the y-axis. Okay, let me just use a quick notation here to just symbolize that it is going to be a reflection about the y-axis. Okay, but we should be describing in words in our actual solution. It is a reflection about the y-axis. And from here, I'm going to try to get this 2x plus 1 by replacing x again. Okay, let's take note, okay? We should only be touching x, okay? This is the rule. We don't define the rule by, 2x, okay? I'm going to just plus 1 to it, okay? Then there's no rule. Then you can do anything to the transformation. So the sequence of transformation is when I try to replace x. Okay, so if I were to replace x again, what I'm going to do is to replace this x here by x plus half. Because by doing so, it will give me a 2x if I were to expand it, plus 1, which is this expression here. So I replace x by x plus half, replacing x by x plus half. So this will cause the transformation to be, it is going to be a translation of half units in the negative x direction. So the transformation will be this, half units in the negative x direction. And one last transformation, because the question asks for 3 transformations to get this. So the one last transformation is to get this plus 5. So I'm going to take this original graph here, original equation here, and I'm going to add 5 to it. Okay, this is easy, and this will get us our final expression, the final graph that we are supposed to getting. So plus 5, this is going to be a translation of 5 units in the positive y direction. Okay, we have completed question number 1. Let's move on. Let's take a look at question number 2. Question number 2 is a very interesting question to me because of this unknown k that is going to be defined in 2 ways. Okay, let's take a look at it. Question number 2, the equation C is given to us as y squared plus k x minus 3 squared. This is equal to 4, and k is a real constant. Part A. Part A, we are supposed to sketch the graph of C when k is bigger than 0. And then we are going to sketch another graph where k is less than 0. So let's be sketching 2 graphs, okay? So when k is bigger than 0, if k is bigger than 0, this plus k x minus 3 squared, this is equal to 4, where k is bigger than 0. And what I'm going to do is I'm going to divide this 4 across to the other side, which will then give me a y squared over 4 plus k of x minus 3 squared over 4 is equal to 1. Can you guys guess what this graph, what this equation is going to be representing? What kind of graph am I going to be deriving at? It is going to be an ellipse, correct? It is going to be an ellipse. We just need to do one last manipulation. I'm going to write x first, okay? So x minus 3 squared. This k, let's move it to the denominator, which will give me a 4 over k. So divided by 4 over k. 4 over k, I'm going to write it as 2 over square root of k square. Okay, this is the 4 over k. As for this is going to be plus y square over 4, which I'm going to write it as 2 square. This is equal to 1. So this is an ellipse. So let's sketch this ellipse. This is an ellipse with the center at 3, 0, and with a horizontal radius of 2 over square root of k and a vertical radius of 2. So let me draw this ellipse. This is the x-axis. Let me just draw the ellipse first, okay? So on this x-axis, we have something that is like this to represent the ellipse. It is totally okay if you want to draw the ellipse this way. Okay, the how do I describe it? The taller ellipse, then the more, I'm drawing the wider one, okay? But both are okay. So it is going to be this. The center here is going to be at 3, 0. And the vertical radius is 2. So 3, 0, it will become this point. The highest possible point here is 3, 2. The lowest possible point here is going to be 3 and minus 2. The horizontal radius is 2 over square root of k. So this point here is going to be 3 plus 2 over square root of k, 0. This point here is going to be 3 minus 2 over square root of k, 0. I guess we can draw the y-axis anywhere. I don't think it is possible for us to determine whether the y-axis is here or whether it is here. So it doesn't really matter. I'm going to just go for here, let's say. Okay, so this is going to be my y-axis. This is going to be the x-axis. So we have this, and we are supposed to also sketch the case where k is less than 0. Okay, let's sketch the case where k is less than 0. So for B, we are sketching this again. K, x minus 3 squared, this is equal to 4. But this time k is less than 0, okay? And this is the one that is very tricky, but yet it is also very valuable for us to do a question that is like this, because it just trains us to be more sensitive to numbers, to algebra, to constants that are given to me. Instead of numbers, they are given to me as alphabet. But definitely in the exam, if we start to get a little bit confused, okay, we can definitely try to use an example, a specific example to help us to identify the original graph that to identify the way that I can draw the graph, or to just give myself an insight on how I'm going to carry out the manipulation. This, I think it is still not too bad because k is bigger than 0. But what if k is less than 0? Okay, so I'm going to imagine this, okay? So if I were to let k be a number that is less than 0, let's say minus 5. Okay, minus 5 is less than 0. So this will become y squared minus 5 x minus 3 squared. This is equal to 4. Okay, to me, this becomes obvious. It is going to be a hyperbola. So I'm going to try to manipulate this so that I can get a hyperbola. So from here, I'm going to divide by 4 throughout, which will give me a y squared over 4 minus 5x minus 3 squared over 4. This is equal to 1. But I've actually carried out a process here, which is this minus 5. I've actually broken up into two parts, minus and the 5. So minus, I let it continue to be outside. 5, I brought it in. And now I will rewrite this as 2 squared, and 5, I'm going to bring it to the denominator. So I have x minus 3 squared divided by 4 squared, which is 2 squared, and square root of 5 squared, which will give me a 5. So if I can just rewrite it into a form that is like this, okay? 2 squared is going to give me a 4, square root of 5 squared is going to give me this 5 over here. So I know this is going to give me this hyperbola that I was just saying. We have already known the equation of hyperbola, so we should be able to guess this in the exam. So now I'm going to try to apply my experience here, which was actually easier, to now k, which has hidden that negative, okay, because k is a negative number. So if I were to just make use of this to inspire me in the exam, okay, I mean, sometimes we do want to use strategies that is like this. Or else, I mean, it is better to do something that looks a little bit basic, looks a little bit like not as professional, but we will be getting the answer correct, which means that we actually choose something that is adding a lot of value into the way that we're going to solve problem. And to me, I feel that this is a high level. Okay, this is not something that is degrading. This is good. It helps me to process. So y squared plus k, like what we have experienced here, we're going to extract out the negative. So it will be negative of negative k. X minus 3 squared is equal to 4. And please take note, since k is less than 0, negative k is going to be positive now, okay, which behaves like this positive 5 over here. And 4, if I were to divide across, I will have this. Then minus, we have a minus k, x minus 3 squared over 4. This is equal to 1. It's synchronized to this. This 5 is like this minus k. Right? Minus 5, it gives me this 5. So now, rewriting this, y squared over 2 squared minus x minus 3 squared over 2 over square root of minus k squared is equal to 1. In case you start to get confused, minus k, where k is less than 0 is a positive number, so it is totally okay to square root this minus k because I'm going to be getting a real number. So now this is going to be a hyperbola. It is a hyperbola which will have asymptotes. Let's work on the asymptotes first. The asymptotes for this hyperbola, let's just work on the labeling of the asymptotes. Okay, let's try to come up with the equations of the two asymptotes of this hyperbola. And from what we have memorized about the asymptotes, it is going to be y is equal to 2 over square root of minus k of x minus 3. So the asymptotes will be y is equal to plus or minus, sorry, I missed out plus or minus here, plus or minus square root of minus k and x minus 3. Let's sketch this hyperbola with the two asymptotes. So I'm going to sketch in my x-axis here, and my y-axis, let me just sketch it here. My y-axis. The center is at 3, 0. So let's say it is going to be here. The asymptotes will be this, and it will be this plus or minus. So let me sketch in the asymptotes first. We have this, and we have this. Okay, this will be y is equal to minus square root of minus k x minus 3. And this will be y is equal to positive square root of minus k x minus 3. And the center here, this point here is at 3, 0. And for this version of the hyperbola, it is going to be this and this. So let me sketch it in. So we have this. The turning point is directly above this. And it should be tending towards the asymptote. And the other one is going to be like this. Again, the turning point is directly below this. And it will tend towards the asymptote. And this point over here will have a coordinate of 3. The vertical height is going to be 2. So 3, 2. And here, the vertical height is 2. So here it's going to be 3 and minus 2. So this will be my second graph. Next, the question says, assume that k is between 0 to 1. So we are looking at this case here, okay? K is between 0 to 1 is when k is bigger than 0. Assume that k is between 0 to 1. We are supposed to look at this region S that is bounded by the curve C. So we are looking at a graph that is something that is like this. By the curve C, x is equal to 3, which is here. X is equal to 3. And x is equal to 4. Okay, x is equal to 4, we do have a bit of a problem. X is equal to 4, okay, because we need to know whether 4 is here when it is still within the width of the hyperbola, or is 4 outside the width of it. So let's do a quick check. So the question tells me that k is between 0 to 1, okay, which is this. So k is between 0 to 1. So if k is between 0 to 1, that means if I were to do a square root of k, because I'm trying to analyze this, the coordinate of this, okay, because 4 is definitely going to be on the right hand side. So I'm going to analyze this, which is this 2 over square root of k plus 3. So I want to look at this square root of k. Square root of k is going to be between 0 to 1 also. So square root of k will be a number that is like half. And what is 1 over half? 2. What is 1 over 3? 3. So if it is going to be 1 over square root of k, it's going to be a number that is going to be bigger than 1. So if I were to multiply by 2, this is going to be bigger than 2. If I were to plus 3 to it, 3 plus 2 over square root of k plus 3, this is 5, which means that 3 plus 2 square root of k is a number that I'm expecting it to be bigger than 4, because it is going to be bigger than 5. So 4 is going to be somewhere here. So let me try to shade this region, according to what the question says, this region S. So it's going to be from here all the way. Okay, x is equal to 3 and x is equal to 4. Let me go for somewhere here. So this line here is x is equal to 4. So we are looking at this region. And the question says that this region here is going to be rotated by 180 degrees with respect to the x-axis. So for this region, which is actually symmetrical, how do we know that it's symmetrical? Because it is an ellipse. Okay, we have already studied the shape of an ellipse, so it is going to be symmetrical about the center. So this shape here is symmetrical about the x-axis. So just by rotating it 100 by 180 degrees, we will be able to get a complete solid. Okay, it is not half of it, because this entire part is going to be rotated. Okay. If it is just the top portion, yes, if you have to rotate it by just 180 degrees, then you're going to get half of the solid. But the full thing, where it is symmetrical, the top and the bottom, when it is rotated, we're going to get a full solid. So we're going to try to find the volume of this. And I'm going to make use of integration. And to make use of integration, we need expressions that are we need expressions that are of functions in nature. But this is not a function, or these are not functions. So I'm going to try to break up the graph into parts, break up this equation into parts. So this is going to be equal to 4 minus k of x minus 3 squared, which means that y is going to be plus or minus square root of 4 minus k x minus 3 squared. And we are looking at, I'm going to just look at the top portion of the graph. Okay, which means that I'm going to be working on just this part of the graph here. the top portion of the graph, let's say I include the two ends here. So I'm going to be working on this portion of the graph from 3 all the way until 4. And I'll take this portion of the graph and I'm going to rotate it with respect to the x-axis. It will give me the volume that the question is describing. And for this part of the graph, the equation is y is equal to plus minus y. So the top portion is going to be plus y, the bottom portion is going to be minus y. So here it's going to be positive square root of 4 minus k x minus 3 square. So now we can find the volume. This is B part 1. Okay, so in part 1, the volume is going to be pi integrating from 3 to 4 of this square root of 4 minus k x minus 3 square. Okay, this is an easy integral to perform, integration to be performing. So this will be pi 3, 4. We will have this as just simply a 4 minus k x minus 3 square dx. So pi, we can already start integrating. Integrating 4 gives me 4x. And integrating this gives me a x minus 3 cubed divided by 3 to 4. Substituting 4 in, we'll be getting a 16 minus k over 3. Substituting 3 in, we'll be getting a 12. So my answer for this is going to be equal to pi of 4 minus k over 3. Okay, I guess this is not too bad. Okay, we did do a bit of analysis here, but I think that's okay. Next, it is a 1 mark question. The curve C is going to be then stretched with a scale factor of half parallel to the y-axis. It's going to be stretched by a factor of half parallel to the y-axis. And we are supposed to, without carrying out any further integration, we are supposed to find the volume of this new curve. And for the region that is bounded by this new curve and the line x is equal to 3, the same line x is equal to 3, and x is equal to 4, and it is going to be rotated by 180 degrees with respect to the x-axis. Okay, and we are supposed, and it is just 1 mark, which means that we are expected to almost quote or state the answer for this last part. Let's take a look at the equation that we will be expecting. Because it is going to be scaled by a factor of half parallel to the y-axis, which means that for part 2, let me just write it down here, okay? For part 2, the new equation is going to be plus or minus half square root of 4 minus k x minus 3 square. Okay, I just need to multiply half to it because it is going to be scaled by half parallel to the y-axis, which means that the volume for this particular graph is going to be pi integrating positive half. Okay, I'm going to be taking the top portion. It is just actually this scaled by half. Okay, compressed. Okay, it's going to be scaled by half. So it will have the same width. It is just going to be compressed by half. Okay, against you from 3 to 4. So 3 to 4. And this is this square root of 4 minus k x minus 3 square dx. So this is going to be the integral that represents the volume that is going to be generated through the new transformed graph. And for this, let me erase this a little bit, okay? I just realized something. I shouldn't have erased this because I will be needing this. So let me just rewrite this again, okay? This is this integrating from 3 to 4 of square root of 4 minus k x minus 3 square dx square. And this will result in this 3 to 4 of 4 minus k x minus 3 square dx. Okay, I'm so sorry. We actually do need this because from here, we actually will get a version of this. Okay, that's why I need this to be still a reference to us. So if I were to square this, I will have a pi 3 to 4 half square. It will give me 1/4, which I'm going to subsequently take it out. And I'll have this 4 minus k x minus 3 square. 1/4, when I take it out, it is going to be this. then it will be 3, 4. And we have a 4 minus kx minus 3 square dx. So what we have now is a 1/4 of pi integrating from 3 to 4 of 4 minus x minus 3 square dx. We have this, and this is exactly this that I accidentally erased just now, which means that we already have the answer to this integral. It is this. That is why my answer is supposed to be just this multiplied to 1/4. So my answer to this is going to be pi over 4 of 4 minus k over 3. Okay, and for those of you who are able to just know at a glance that this half is going to be squared, because it is going to be squared, the original one is going to be multiplied by 1/4, the original volume is going to be multiplied by 1/4, you can just state the answer without having to even write down any working, because this question here is worth just 1 mark. Let's take a look at question number 3, this one here. This is a Maclaurin's question. So for question number 3, we are given 4 plus x squared divided by square root of 4 minus x. We are supposed to expand this in ascending powers of x. Not too tough. Question number 3a, 4 plus x squared divided by square root of 4 minus x. I can rewrite this as 4 plus x square 4 minus x to the power of minus half. So I'm going to carry out a binomial expansion, specifically the Maclaurin's version of the binomial expansion here. So I need the first term to be 1. Let's factorize out 4, so it will be 4 to the power of minus half. Then 4 plus x squared. This, it will be 1 minus x over 4 to the power of this. This is going to be 1 over 2, and we have here as 4 plus x squared still. This, let's try to do an expansion to it. It is going to be 1 plus minus half minus x over 4 plus minus half minus 3 over 2 divided by 2 factorial minus x over 4 square, and all the way until infinity, because we are supposed to expand this all the way until the x to the power of 3 term. Sorry, x to the power of 2 term. So I'm stopping at this x. I'm stopping at this square. So this is equal to half 4 plus x square. And this, simplifying it, I have a 1 plus x over 8 plus 3 over 1 to 8 x to the power of 2, and all the way until infinity. And let's do another round of expansion. 4 times 1 is 4. This times this gives me a x over 2. Then this times this gives me a 3 over 32x squared. This times this gives me an x squared. This times this, and for the rest of the terms, they're going to be more than x to the power of 2. So I'm going to leave the rest of the terms just in the dot dot. So simplifying this, we will be getting a half of 4 plus 1 over 2x plus 3 over 32x squared. So in fact, let me just multiply the half in directly. So this times this is going to give me a 2. This times this gives me a 1/4 x. This times this plus this gives me a 35 over 64 x squared, and all the way until infinity. This question went on to ask that we are supposed to ask us for the set of values of x such that this expansion is valid. So for this expansion to be valid, it is through this over here, where we carry out our Maclaurin's expansion. So for this over here, for it to be valid, we want to make sure that modulus of x over 4, it must be less than 1. which means that modulus of x, it must be less than 4. So x is going to be between minus 4 and 4. And since the question asked me for the set of values, so I'm going to just reply with a set notation. X here are all real numbers, such that x is between minus 4 and 4. This is for part A. Let's move on to look at part B, where we are supposed to make use of some differentiation to complete this Maclaurin's expansion. So we are now given in question number 3b, y is equal to ln 1 plus sine x. And we are supposed to show in part 1, we are supposed to show that equation. And in that equation, we have a d square y dx square. So I'm going to do a bit of improvisation to this first. For example, one improvisation that I can try to to modify this is to try to rewrite it into a form that is like this. Okay, my hope is that the process of differentiation will be easier. But of course, you can do this question without doing this improvisation. Maybe you guys can try, but I'm going to just try from this direction, okay? So taking this, I will differentiate it with respect to x. On the left-hand side, it is going to be e to the power of y. Implicit differentiation is going to be performed, so I have this. Then differentiating sign gives me a cosine x. I'm going to differentiate this again. So this will be product rule, d square y dx square plus e to the power of y dy dx. From product rule, I will still need to write down the second term, and this is minus sine x. This minus sine x is good because I can see that it is on the right hand side of the equation that I'm supposed to show. And for d square y dx square, it is supposed to be multiplied to 1 plus sine x. And I guess we can replace e to the power of x by 1 plus sine x. So this, I'm going to replace it by 1 plus sine x d square y dx square. And if I were to just compare this to what the question wants me to show, it is going to be cosine x multiplied by one single dy dx. So if I were to just retain one single dy dx for this, it is actually cosine x, okay? E to the power of x dy dx is cosine x. So this, I'm going to replace it by cosine x. Then we have our dy dx. This is minus sine x. Okay, this is what the question wants me to show, so shown. And in part 2, this is part 1. And in part 2, by further differentiation of the result that is in part 1, we are supposed to find the Maclaurins of y up to and including the x to the power of 3 term. Up to and including x to the power of 3 term. So for x to the power of 3 term, we need d cube y dx cube. And now we have only a d square y dx square. Let's try to differentiate this one more time. So differentiating this again, it is going to be 1 plus sine x d cube y dx cube, product rule. So cosine x d square y dx square. Differentiating this, again, I'm going to be executing product rule. D square y dx square minus sine x dy dx is equal to minus cosine x. We can combine these two together. So let me just do a quick simplification to this. This is 1 plus sine x d cube y dx cube plus 2 times of cosine x d square y dx square minus sine x dy dx. This is equal to minus cosine x. And now we are ready to find part of the coefficients of this Maclaurin's expanded form. So I'm going to let x be equal to 0. And when x is equal to 0, let's find y. This will give me f0. So y is equal to ln of 1 plus 0. So y is equal to ln 1. No, y is equal to 0. And dy dx, let me make use of this. Dy dx will be cosine 0. Cosine 0 is 1 over e to the power of y, which is 0. E to the power of 0 is 1. So this is 1. D square y dx square. D square y dx square is going to be minus sine 0, which is going to be 0. Then minus cosine 0, which is 1. dy dx, it is also 1, divided by 1 plus 0, which is going to be 1. So d square y dx square is minus 1, and d cube y dx cube, this is going to be minus cosine 0, which is going to be minus 1. This is going to be 0, so 0. This is going to be minus 2 cosine 0, which is 1. D square y dx square, which is minus 1. And this is going to be divided by 1 plus 0. So this will be 2 minus 1 divided by 1. This is going to be equal to 1 d cube y dx cube. So therefore, I can now find y. Let me write it here. Therefore, y, which is this ln of 1 plus sine x, is going to be equal to, this is 0. So it's going to be equal to 0 plus f prime 0, which is 1, x plus f prime prime 0 minus 1 divided by 2 factorial x square, and this is going to be 1 divided by 3 factorial x to the power of 3, and all the way until infinity, this is going to be equal to x minus 1 over 2 x to the power of 2 plus 1 over 6 x to the power of 3, and all the way until infinity. So this is the result that I've gotten for part 1. Let me just write it down here because we are going to be using it for the next part. X minus 1 over 2x squared plus 1 over 6x to the power of 3 all the way until infinity. And in the next part of the question, the last part of the question, it says hence. So I do need to make use of the previous result here. Hence, we are supposed to find the Maclaurins of another expression which looks somewhat similar to the one that we have just expanded. Let's try to write them like side by side so that we can do a comparison. The one that we are supposed to expand now looks like this in part 2. It is this ln of 1 minus sine x divided by 2. And it's very, very easy for us to remove this 2. Right? We just need to apply the law of logarithmic function. This will be ln of 1 minus sine x minus ln 2, which is a constant, and that is fine. It is just going to be part of my expanded version for this. As for this, I'm definitely going to make use of the previous part. And in order for me to make use of the previous part, we need to apply trigonometric transformation, because minus sine x is same as plus sine minus x. This was what we have learned in our secondary school. Minus sine x is equal to sine negative of x. So this is going to be now this, where x is going to be replaced by minus x. So it's going to be minus x minus 1 over 2 minus x squared 1 over 6 minus x to the power of 3, and all the way until infinity minus ln 2. Let me just write down minus ln 2 in front. Okay, so we will have a minus ln 2 minus x minus 1 over 2x squared minus 1 over 6x to the power of 3. And let's not forget about this, all the way until infinity, because we are doing a Maclaurin's series, which aim is to re-express it into an infinite polynomial. An infinite polynomial. Okay, let's move on. The last pure math question before the statistics portion is going to start. So let's take a look at this, question number 4. Vectors. Okay, for question number 4, we are given 2 planes, P1 and P2. In the first part, we are supposed to show that P1 and P2, they are perpendicular to each other. I guess this is easy. We just need to take the 2 normal vectors and dot them together. If they give me a 0, then if the result of their dot product gives me a 0, then they are perpendicular to each other. For P2, it is very easy for us to extract the normal, which is 4, 1, 3. For P1, we do need to do a bit of calculation. For P1, I'm going to call is normal. This is question number 4. For P1, I'm going to call its normal N1. And for N1, I will just take 1, 3, minus 2, cross 1, 0, 1. Okay, we are taking these two vectors which are parallel to the plane. Crossing them should give me the normal vector to the plane. And this gives me a 3 minus 3 minus 3. And I'm going to just simply factorize out minus 3. So I'm going to look at its normal as minus 1, 1, 1. Okay, this is a more simplified version. It is definitely more friendly in terms of calculation. As for the second normal, the normal to plane P2, I am going to just extract out directly from the Cartesian version that is given, which is going to be this 4, 1, 3. So let's do a test to just check whether these two planes P1 and P2, they are perpendicular to each other. We'll take the two normal vectors, minus 1, 1, 1, cross 4, 1, sorry, dot 4, 1, 3, to check whether it is going to be whether they are going to be perpendicular to each other. So for this times this gives me minus 4 plus 1 plus 3, this gives me 0. Therefore, we know that P1 and P2, they are perpendicular to each other. Okay? You guys can fill in the statement. So then part 2. Part 2, we want to explain why is it that L passes through the point 1, 0, 1. And we want to find the vector equation of this L. What is this L? L, according to what the question says, L is the intersection between the two planes. So the two planes will be intersecting at a line. This line is called L. And if 1, 0, minus 1, if 1, 0, minus 1 lies on L, that means 1, 0, minus 1 must also be lying on both planes P1 and P2, correct? So let's try to verify by substituting this point 1, 0, 1 into both P1 and P2. And if it satisfies both equations, it tells me that this point 1, 0, 1 also lies on the line L. For P1, let's try to convert it into the dot product form. So for P1, it will be R dot, the normal vector which I chose it to be this, minus 1, 1, 1, is going to be a point. I'm going to make use of the position vector of a point that is on P1, and from the equation, I'm going to use this point, the position vector of this point here. So it is going to be 0, 3, and minus 5. So this dot minus 1, 1, 1 will give me a 3 minus 5. This is minus 2. So this is the dot product version of the plane P1. For P2, this will be R dot 4, 1, 3. This is equal to 1. So let's try to verify whether this point 1, 0, minus 1 truly lies on both this plane, and then we can conclude that it lies on the line of intersection between the two planes. So I'm going to take this point, 1, 0, minus 1, and I'm going to sub it into the equation of this P1. So this dot minus 1, 1, 1 on the left hand side, we have a minus 1 plus 0 minus 1, which is minus 2. Therefore, we can conclude that 1, 0, minus 1 lies on the plane P1. This, I'm going to call it my statement A. I'm going to test 1, 0, minus 1 again, and I want to test whether it lies on the plane P2. So 1, 0, minus 1 dot 4, 1, 3. This is going to be equal to 4 plus 0 minus 3, this is equal to 1. And therefore, we can say that 1, 0, minus 1 lies on the plane P2. And this, I'm going to call it my statement B. So from A and B, this tells me that the point 1, 0, minus 1 lies on the line L, which is the intersection between the two planes P1 and P2. And we want to find the equation of this line L. Okay, there are two methods for us to do that. Of course, the easier one is to convert this into the Cartesian form and take the Cartesian form of the plane P2. I will press this into the calculator, then from the calculator, I'm going to just read off the line of intersection between these two planes, which can be representing the vector equation of this line L. Okay, so that is one method. You guys can go and try it. But I'm going to use one that is a little bit more, that require a bit more of visualization. So I mean, it's not the easiest, but it's actually more efficient if you are able to visualize that for this particular case. Because for part 2, we are looking at a scenario that is like this. Okay, let's say this is plane P1. And let's say we have plane P2 as this. P2. Okay, we have determined that they are perpendicular to each other. And where is the line L? The line L is going to be here, right? This is the line L. And we already know that this line L has a point. The point is this 1, 0, minus 1. So what we need in order for us to form the equation of this line L is a direction that is parallel to L. And for this direction, we can actually take the normal vector to plane P1. I'm going to call this N1, which is not this N1 here, okay? It is actually this, but more for our visualization. So this N1 here actually represents this. Then N2 is going to be the normal vector to the plane P2. And if I were to cross these two vectors, okay, this will require some visualization. Okay, if I were to cross these two vectors, I'll be getting a vector that is perpendicular to the original two vectors. And this vector will be actually parallel to L. So if you are able to see this, it is going to be way faster because I just need to take minus 1, 1, 1, which is the normal vector that I'm going to be using for the plane P1, cross 4, 1, 3. If I were to take this cross this, I'm going to be getting a 2, 7, minus 5. And this will help me to get a vector that is parallel to L, which means that L will look like this. R is equal to the position vector of a point that is on L. We have already verified that this point lies on L, plus, since the question has already used lambda and mu here, okay, I'm going to avoid lambda and mu. Let me just use gamma. So plus gamma of 2, 7, minus 5. So this is the equation of the line L. This is part 2. Part 3, we have this point A, which lies on P1. I don't know where it is, so let's say it is here. Okay, this is point A that lies on point P1. B lies on point P2, so let's say it is this B. And we have the coordinates of A and B that are given. And B prime is the reflection of B in the line L. L is this. So B prime is going to be a reflection. We are talking about something that is like this. Okay, so let's say there's a point here. It is a reflection. So B prime is going to be something that is like this, where this distance is the same as this distance. We are supposed to find the exact area of the triangle A, B, B prime. So this. Okay, we are supposed to find the area of this triangle. Area of triangle, half of modulus of taking the vectors of two sides and I'll cross each other, half of modulus of the cross product of these two vectors. So we are going to try to find the two vectors. So I will probably need the coordinates or the position vector of point B prime because we already have the coordinates of A, coordinates of B. So if I can also have the coordinates of B prime, then we can find AB. We can find AB prime, and we will take these two cross each other, and we are going to be able to derive the area from there. So I'm going to try to work on this aspect. Let me just state for myself the information that I have so far, okay? So for P1 is R dot minus 1, 1, 1 is minus 2. For P2 is R dot 4, 1, 3, this is equal to 1. And L is this. R is equal to 1, 0, minus 1 plus gamma of 2, 7, minus 5. Okay, let me erase away the rest of the things that I've written. We'll probably need some space to do this question here. It is a 5 marks question. By the way, there are a few different ways to do this question. Okay, so I'm going to be just showing one of them on the board here, but go ahead and explore the other possible ways that you can solve for part 3. Okay, there are a few different ways that I can really think of as I'm looking at this part 3. So anyway, I'm going to first work on this point here. This point. I'm going to call this point here F. F is the foot of the perpendicular from B to the line L. F is also the foot of the perpendicular from B to the plane P1. Okay, F is the foot of the perpendicular from the plane B to the plane, from B to the plane P1. So let me just, since it's a typical and classic scenario, I'm going to just redraw my diagram, okay? So it is going to be like B over here, then the plane P1. Okay, plane P1 is r dot minus 1, 1, 1 is minus 2. So we are going to try to find point F first. The foot of the perpendicular from a point to a plane. So this is having a coordinate of 2, 2, minus 3. Which means that I can find very easily the line that passes through B and F. This line will pass through point B, 2, 2, minus 3, plus, I need another constant here, another variable here, so I'm going to use rho. And I need a direction that is parallel to BF, and a direction that is parallel to BF can be very easily obtained by looking at the normal to P1. Right? The normal to P1 should be parallel to BF. So I'm going to go for minus 1, 1, 1 here. And since F is a point that lies on this line, so OF is going to adopt the form of this, which is 2 minus rho, 2 plus rho, minus 3 plus rho. But F is also a point that is going to be on P1. So this position vector should also satisfy this. So which means that OF dot minus 1, 1, 1 should be equal to minus 2. So 2 minus rho, 2 plus rho, minus 3 plus rho, this dot minus 1, 1, 1, this is minus 2. So we have a minus 2 plus rho plus 2 plus rho minus 3 plus rho. This is equal to minus 2. We will be able to solve for rho here is equal to 1 over 3. And now we can find OF. Let's find OF. Therefore, OF is equal to 2 minus 1 over 3, 2 plus 1 over 3, and minus 3 plus 1 over 3. And OF is going to be equal to 5 over 3, 7 over 3, and minus 8 over 3. And now I'm going to make use of the fact that I know B, F, and the proportion of B prime F, F to B is a proportion of 1:1. I'm going to make use of ratio theorem to find OB prime. So let me just redraw the diagram just for my visualization's sake. B prime, let me draw it here, then F here, and B here. And since they are reflection, since B and B prime, they are reflection about this point F, so this is going to be 1:1. I'm going to reference everything to the origin, and let's try to apply the ratio theorem. So applying the ratio theorem, OF here is going to be 1 time of OB plus 1 time of OB prime divided by 1 plus 1. So OB prime is going to be equal to 2 times of OF minus away OB. So it's going to be 2 times of 5 over 3, 7 over 3 minus 8 over 3 minus away OB, B. Okay, B is here. So minus away 2, 2 minus 3. OB prime, let me give you the position vector of it, is 4 over 3, 8 over 3 minus 7 over 3, OB prime. And now we have obtained all the necessary coordinates of the points that of the triangle where the area I'm supposed to find. So for this triangle, okay, this is not exactly what I'm seeing here, okay, but anyway, this B prime and B, we're going to make use of this vector and this vector, okay. We're going to take these two vectors and cross them one with another. So let me find AB first. AB is going to be OB minus OA. AB is going to be OB. OB is 2, 2 minus 3 minus away OA, which will be 0, 3 minus 5. This is given to us by the question. And this is equal to 2 minus 1, 2. I'm going to find AB prime. And AB prime is going to be equal to this. So 4 over 3, 8 over 3, minus 7 over 3, minus OA, which is 0, 3 minus 5. And this is equal to 4 over 3, minus 1 over 3, and 8 over 3. And now we can find the area of this triangle. This triangle, according to how the question name it, it is ABB prime. So the area is going to be half of modulus of AB cross AB prime. So it's going to be half of modulus of AB, which is 2 minus 1, 2, cross AB prime, 4 over 3 minus 1 over 3, 8 over 3. It's going to be half of, performing the cross product here, we'll be getting a minus 2 minus 8 over 3 and 2 over 3. And this will get us a half of square root of 104 over 9, which you will be able to work this out to be equal to square root of 26 over 3 units square for the area. And now comes the third plane, P3. Let me write down P3. This third plane, P3, is R dot A31 is equal to minus 9, where A is a constant. And the point Q lies on all these three planes at the same time, P1, P2, P3. Part 4, can we explain why Q lies on the line L? Obviously, right? Because Q lies on all the three planes, which means that Q will be lying on both P1 and P2. If Q lies on both P1 and P2, that means Q must be lying somewhere that is on the line L. Okay, so this is the reasoning. Q lies on P1 and P2. Therefore, Q lies on L. Part 5. Hence or otherwise, we are supposed to find the coordinates of this point Q. So Q lies on the line L. Okay, Q lies on the line L. That means OQ is going to look something that is like this. So OQ will be 1 plus 2 gamma, 7 gamma, and minus 1 minus 5 gamma. OQ lies on L. And Q also is a point that is going to be lying on P3, because according to what the question says, Q lies on all the three planes. So since Q also lies on P3, the position vector of Q should satisfy the equation of P3. So OQ dot A31, this should be equal to minus 9, which means that 1 plus 2 gamma, 7 gamma, minus 1 minus 5 gamma, dot A31, this should be equal to minus 9. And this makes us feel a little bit uncomfortable because we are supposed to solve for the coordinates of point Q, right? And in order for me to solve for the coordinates of point Q, my aim now is to find a value for gamma. But here we have two unknowns, okay? So let's see whether it is possible for us to be resolving this. And our aim is to try to make gamma the subject, because we are supposed to find the value for gamma. So this will be A plus 2A gamma plus 21 gamma minus 1 minus 5 gamma. This is minus 9. And we have A plus 2A gamma plus 16 gamma. This is equal to minus 8. Okay, let's just try to make gamma the subject, because that's what we are supposed to do. Okay, although it feels awkward because I don't want to have gamma in terms of A. We are supposed to try to solve for the coordinates of point Q. But let's just make gamma the subject first. This will be gamma of 2A plus 16 is minus A minus 8. So gamma is equal to this, minus A minus 8 divided by 2a plus 16. In fact, we can simplify this. Can you see this? Okay, it is like minus a plus 8 divided by 2 times of a plus 8. So cancel. This actually gives me a value. Okay, this is what I'm hoping for. This gives me a value for gamma. Gamma is equal to minus 1 over 2. Therefore, we can find Q, the position vector of Q. OQ will be 1 plus 2 times of minus half. Then 7 times of minus half. And minus 1 minus 5 of minus half. So OQ is going to be, OQ here is going to be equal to 0 minus 7 over 2 and 3 over 2. The question asks us for the coordinates of Q, so therefore Q will have a coordinate of 0, minus 7 over 2 and 3 over 2. And that helps us to end the last question in pure math for our section A.